record. Your recording has started. I'll share the screen. Yeah, over to you, Mansi.
Should I start? Hello, we are Team CodeCube presenting language detection model. And in our team, there's me, Kaylee, Neil, and Nick. So we'll start with project overview. Next, thanks. For the project overview, we are building language detection model where we have used audio files and the model will be capable of distinguishing audio spoken in English, French, and Spanish. Here we have used CRIPS DM methodology for building the model. And the reason behind choosing this model is that this model will act as the part of translation, which can allow people from different parts of the world to communicate with each other. To build this model, it is important to understand about business understanding. So here we want to build language recognition model that can identify audio presented in English, French, and Spanish. The target is to have overall accuracy of 90% for the model, and each class should have precision of greater than or equal to 90%. And model should be able to deploy on low-powered system without needing GPU for inference. Now Kaylee will continue with data understanding part.
All right, so for step 2, as Monsi mentioned, we went with data understanding, and for our main data source, we used an open source audio corpus data that was available on Common Voice. So this website just has an archive of different audio files from different languages. And for our specific project, we decided to go with the English audio, French audio, and Spanish audio. Next slide, please. So continuing on, these are just some statistics for the data that we used. For the amount of recorded hours, for English, it was 70. For French, it was 80. And for Spanish, it was 52. As for number of voices, there were 1,212 English voices, 1,697 French voices, and 373 Spanish voices. For number of files, there were around 44,000 English files, 75,000 French files, and 36,000 Spanish files. The average length for English was 5.7 seconds. For French, it was 3.7 seconds, and for Spanish, it was 5 seconds. And as for sampling rate, amongst all of the languages, there were 22,050 hertz. All right, now I'm going to go into our data pre-processing step. So for the first step, we wanted to arrange all of the audio files into a proper folder structure. Since Google Colab does have a limitation where it'll stop running due to big data, we wanted to make sure we organize all of our data in proper folders and subfolders. Secondly, for each of the audio files, we represented it as numbers and extracted other information such as sampling rate and length of the audio for the files. Then we also generated the mel frequency substral coefficient, also known as MFCC, for each of the audio files, which was around 40 per file. And we also handled class bias and used the MFCC's value for training our model. All right, so now I'm just going to go into why we used MFCCs to train our model. First and foremost, MFCCs are capable of representing phonetically relevant features. And since languages have a lot of phonetic sounds, we thought this was the best method to do so. As for resilience to noise, MFCCs have that capability. And lastly, MFCCs also act as dimensionality reduction, where it was able to represent many files with certain numbers of coefficients, and this was done to prevent overfitting. Now I'm going to pass it to Nick.
So coming into modeling, we will basically be trying to identify a number of neural network architectures to find the model that works best for us. We have two main types of neural networks in mind, and which we tried. We used recurrent neural networks using long-term, short-term memory, as well as a one-dimensional convolution neural network. The reason behind this is that within an audio file, the last data related to the present data and the above two methods are really good at capturing these types of relations. And after some testing, we found that out of all these network models, we found that a 5-layer one-dimensional CNN was best. So looking at our training pipeline, we first took the audio and processed it to be into a form of numbers. We extracted the MFCCs from this and used a one-hot encoding label. From there, we reshaped the data into a 3-dimensional matrix, used this for model training, and then evaluated our results. So evaluating our results using the confusion matrix, we see that the majority of the values fall in the identity or the diagonal axis of the confusion matrix, meaning that the algorithm was mostly successful in properly identifying the language. However, we did have some false positives, although these are small relative to the number of correctly predicted results. And going back to our original goal of creating a model that is able to identify languages with an accuracy of at least 90%, we can see that our precision ranged from 90 to 96% depending on the language, giving us an overall accuracy of 93%, which exceeded our goals.
Now coming to deployment. For deployment, we have used Azure Machine Learning Studio. The first thing we have done is after we finished our training, we got the H5 TensorFlow file. We registered it on Azure Machine Learning Studio as a model. After that, we created a custom environment in which the model will run. This custom environment is nothing but a Docker image of a sort, which the Azure Machine Learning endpoint will run. And along with that, we provided the Azure Machine Learning endpoint and inference a scoring script. This scoring script is what the endpoint will use to get a request, extract the data from it, make prediction, and return the results back to us. Yeah. So this is how the inference pipeline looks for us. This is the deployed inference pipeline. So first thing, this is the client. It could be any application or Colab notebook or anything. So first thing, the client loads the file, generates the MFCCs for it, and asks the Azure Machine Learning endpoint to make the predictions. The endpoint makes the prediction and returns back the result. It would basically return. So we are using softmax layer in the neural network. So it would basically return the probability of it being all 3 languages. From this, the client will extract the value with the index with the highest probability using argmax and perform in reverse one-hot encoding to come back to the language. So based on the 3 probabilities, if English is 1, Spanish is 0.2, French is 0.7, it will find out that English has the highest probability, that's the index 0. It will then apply the inverse on a one-hot encoding on index 0 and find out that 0 represents to English. That's basically how the inference will work. Now, future scope for this project. The future scope includes ability to distinguish more language, handling longer audio files, building an entire application around it, and adding language transcription and translation capabilities. That being said, now it's time for the demo. Okay, we're gonna start the demo. Let me share my screen. So first thing we do is after we downloaded all the files, we need to extract it in the form. We need to extract from all the files. Firstly, we have to once you extract it, what you'll end up having a folder called English, which will have over 7,000, 8,000 files. You'll have a folder called Spanish having 7,000, 8,000 files, and same with French. Now, Google Colab has a limitation. If a single folder has more than 1,000 files, when you try to run a Colab notebook, the drive will automatically dismount in like 5-10 minutes. So to overcome that, what we're going to do is we're going to run the script called move file. So what this will do is basically it will go through all the files and make it and arrange it in a subgroup of 100 file per subfolder. So if you do that, once you run that, you'll end up having something that looks like this. You'll have English. Inside English, you'll have all the subfolders, and each subfolder will have a max of 100 files. And it is just a random arbitrary number which we settled on. And same with French and Spanish. Once you have all the folders in the correct, you have all the data in the correct position and everything. After that, what you're going to do is we want to extract all the audio information from it. So for that, we'll be running something called formatting audio data. What it does is it is going to run through all the data, like all the audio files in each subfolders. It is going to extract the audio data, which is like the numerical representation of the data, the sampling rate, the file length, and the label. That is like if the audio is belonging to English, French, or Spanish, and so on. This is a bit time consuming process. And then once you have that, we're going to be saving everything as a CSV file as well as a pickle file. The reason for a pickle file is the CSV file by itself is a bit sketchy, where it is not able to, since audio file is quite large, this audio itself is over 22,000, the sampling rate is 22,000. The audio file will have about 22,000 numbers representing a single value, which we added as this. It's not being able to it's not able to save it properly. So to overcome that, we save it as a pickle file. Now, the problem with this pickle file is once you have everything encoded, in the pickle file, you get all the information. This single pickle file is about 20 GB in size. This is just for English. So similarly, you'll have that for Spanish as well as French. So once you have all that data, what we're going to do is we're just going to use the CSV file. Even though audio data is not properly formatted in that, it's okay. We can overcome that later. So let's go back to the EDA. Let's perform an EDA on whatever data we have. So this is the EDA. Firstly, we'll check if we have a uniform sampling rate, the overall shape of the data. So we have about, firstly, we check the overall shape of the data. So we have about 150,000 records. Then we'll check for missing values. We do not have any missing values. Then we'll check if the entire data has the same sampling rate. It does, so we don't have to worry about data having different sampling rate and so on. Then we'll check out the average length of audio files. So English files are roughly 5.7 seconds, French files are roughly 3.7 seconds, and Spanish files are 5 seconds. This is a visualization for the same. After that, what we're going to do is we're going to create a box plot for the audio file length for English, French, and Spanish. We can see the quartile range is between 2 and 10 seconds for English, and for French, we have about 3 and 4.5. For Spanish, you have 4.5 to 5.5. And then there are some values which are outside the interquartile range. Next thing we want to do is we want to find the, if like a lot of values are outside the interquartile range, then it might cause a problem. So for that, we need to find out the number of values present outside the interquartile range for each of the class. Here you can see it is about close to 550, close to 750, and close to 400. So as if you remember, the overall data shape is about 15 lakh. Sorry, 150,000. Compared to that, this value is too small. So we do not have to worry about addressing this. And even if the so yeah, we can just move forward. And then looking for class imbalance, we can see French has a lot more, we have a lot more files with labeled as French than we have English and Spanish. This is one thing which you have to keep in mind, which we will address before we start training. Next, come to feature generation. Now, as you know, so MFCC, we are using MFCCs as a sample feature. This is the first feature which we intend on trying on, and if not, we had other features lined up. But this was based on certain research, and we did. This was the best suitable feature. So the reason for selecting MFCC is because it captures phonetical relevant features, resilient to noise, and it acts as dimensional electricity, where any audio data it will convert into a fixed number of coefficients. So what you'll do is you'll for each of the audio files as the same logic which we used for converting it to CSV and pickle in the previous step. Here, what we're going to do is we're going to use the same logic to generate MFC for each audio file. And along with the MFC, once we have the MFC, we are going to generate 40 MFCs. 40 MFC is just a random number. Ideally, people say that beyond 13, there's not enough deviation between the MFCs. So we're going to start with 40 MFCs. However, if after when we further explore and we find out there's a lot of we do not have the MFCs don't have difference after one point, we are going to discard those. So we'll find the MFCs and then we'll average their value over the time axis. And we're going to save the MFCs and the label in the form of a pickle file. This is the pickle file which we'll later use for training. Once we have the MFCs, then for each language, we'll calculate or we'll find out what does the average MFCs value look for. All the 0 to 40th, 1 to 40th coefficient, what do they look like? So we can see there is a difference between all of them. The MFC, the average value for MFC for English is different, for French is different, for Spanish is different. And this for some coefficient they are same, but however, for most of the coefficient, we see there's a clear difference between them. The same thing we try to explore we try to represent using visualization. These are the average MFC's value. So here you can see that for MFC1, English and French are roughly close, but Spanish is extremely different. For MFC2, English and French, all three are different, and so on. We do not plot it for all 10 or 39 MFC coefficient, but just for some formalization purpose. These were the MFCC average MFCC value. Now, what about the individual MFCC value? To compare that, we would be using box plot. So here you can see the box plot. Most of the box plot have different mean, different IQR, and different outlier, which represents to us that there is a clear data contrast which we can leverage to train a model. Now, coming back to here, what we mentioned, that if we see there's not a lot of difference between MFCs, we'll discard over here. But even in the in the 39th coefficient, we found out that there exists a good amount of difference. We do not have 0.00 point something difference. There's a good amount of difference. So we won't be discarding that. We would be using all 40 MFCs for training. Now let's go back to training phase. Now in the training notebook, what we are going to do is we'll read the MFCCs and the labels. We'll perform a label encoder to the label class. We'll save this label encoder for a later purpose. Then we identified that there was a class bias, right? So we are going to treat the class bias by reducing 40% of the French data. So we'll randomly drop 40% of the French data. After that, we are going to, so this is the idea we had, was using UMAP but again, reducing the number of dimensions to just 3 to see if we can create a classification model based on that. But once we tried that, we found that with just 3 dimensions, there is no clear difference between all 3 classes. So this won't give us it won't be any good because we cannot see any clear demarcation of 3 classes. So that's just one thing which we tried. And after that, let's go straight to training. Now for training, we'll be training sets of neural network. As we mentioned during the presentation, we'll be training primarily. First, we started with RNN. So when training neural networks, you need to set up 2 things. One is which loss function which you'll use, and the other is which optimizer you'll use. In our case, we have decided to use the categorical cross entropy loss function. It works really well with softmax layers. So softmax layer is basically when I give my model to make a prediction whether what language it is, it will tell me the probability of that audio being English, Spanish, and French. And based on the probability, I'll select the one with the highest value, and that would be my output. So that's how basically softmax layer works. So loss function works really well with softmax layer. It is a probability distribution. And along with that optimizer, we have used Adam. Based on the search we did, Adam optimizer is a good optimizer to use with the cross entropy loss function, and it provides the best of both world between momentum and RSMS prop. So the first thing we tried to build was a RNN. So here we are just preparing the data so that it is in an acceptable format for RNN, that is a 3-dimensional data, and so on. Now over here, we split the data in train and test set, with test set being 20% of the total size. And after that, we built a three layer RNN. After building the 3-layer RNN, at the end stage, you can see the validation accuracy is 86%. This is good. However, if you remember when during the presentation, we mentioned that we want to build with an overall accuracy of more than 90%. So I see that the model captured most of the variance of the data, but there is still some variance which it wasn't able to capture. So to overcome that, I decided to make I'll go through the variance route while I will increase the variance, while increase the what do you call it, the complexity of model by adding 2 more layers to it. So instead of a 3-layer RNN, I'll use a 5-layer RNN with long-term, short-term memory, and some dropout layers to overcome overfitting. So when we build this, when we test out this model, it is worse than the previous one, where the overall accuracy is 85%. Just a quick walkthrough. Here, the epoch size is 10. So we tried this model, but we didn't get a good result. Now we have 2 options. Either we can make the LSTM even more complex. However, in that case, one of the conditions which we have is that we want to deploy it on a low-cost endpoint without any GPU. In that case, more complex neural network might be slower. So to overcome that, we decided that a one-dimensional CNN would also capture what happened previously as the CNN slides to the window, the CNN slides to the MFCC data. So we decided to use a single dimensional CNN. Now same here, we are preparing the data so that we can pass it to a CNN. Again, train test split 10, 20, 20 and 80. And then firstly, we built a 3-layer CNN. Here we are using a max pooling layer along with a dropout layer to prevent overfitting and reduce the number of not features, number of parameters the neural network uses. And then once we fit the one-dimensional, three-layered, one-dimensional convolution neural network, we find that the test accuracy on the test set is close to, after 10 epochs, is close to 89%, which is better than both our recurrent neural networks. So gives me confidence that I went in the right direction by using a CNN over an RNN. After that, again, the same logic where it is capturing most of the variants, but not all the variants. So one approach is to increase the number of layers. So we tried a five-layer CNN. With a 5-layer CNN, we were able to get an accuracy of close to 93% by the end of in the validation set at the end of 10 epochs. This meets a criteria which we set at the beginning of the project, where we want a model with an overall accuracy of 90%. So now this is the model which we'll use. However, before we confirm it, let's make sure the model is working as expected. So for doing that, we'll evaluate its confusion matrix. We'll evaluate the ROC AOC curve. We'll evaluate the precision recall trade-off and the curve. So let's look at the confusion matrix. You'll see the diagonal axis, which are the true positives. We have a good amount of true positives. We do have some incorrect predictions, but compared to the overall scale of the data, the number of incorrect predictions is too less. So we are happy with this confusion matrix. Now let's look at the precision recall curve. We can look that the trade-off for both is at around 0.9 and 0.1. This is a really good trade-off. So that makes us confident that we are not overfitting and we are happy with this. And then we have the AUC curve. For all three of the classes, we have a good AUC. The area under the curve is more than 0.9 for all of them. So this gives us confidence on our model's capability. Now, once we have the model ready with us, let's say we finalize this model, we have crossed the evaluation phase of this PM, and now we want to go to the deployment phase. So for deployment purpose, we are using Azure ML Studio. Primary reason because for a new account, you have $200 free credit. So we could just use it directly. So first thing we're going to do is we created our own custom environment. This is, as I mentioned during my presentation, that it is just a glorified Docker container, nothing more than that. So if I go to the context, you can see it's just like basic packages which are required for the model to run and required by Azure and so on. And then we download a model and we register the model over here. When I register, basically we just give it an artifact, like when we upload it, you just give it the model file and this is the registered model. After that, we create an endpoint. Endpoint is basically delivering the model in the form of an API service, a REST endpoint. So you use the model which you created, you use the environment which you created, and you give it a scoring script. The scoring script is basically just the logic which server will run for making the predictions. Let me give you a look on what the scoring scripts looks like. If I go over here. So yeah, so basically when you initialize, it reads the model from the directory, it loads the model in the memory, and then every time you get a request, it extracts the data from the request, reshapes the data into a NumPy array, which the model can use, makes the predictions and return the results to us. That's basically score script. So you'll provide the score script, the environment which you created. Over here, you can see the environment. Yeah, the environment and the model. Over here, the model is like the model which you registered. And based on this, you'll deploy it. Once the model is deployed, let's look at the inference. So there are two ways you can perform the inference. One is the local inference, which is basically just uploading, like loading the model locally, passing it data and getting the predictions. The other is using the endpoint. Now let's look at the first file which you want to test. Let's look at the French data.
À quoi ça sert de les écouter?
You can see that like the data is in, you can hear the data is in French. So what we're going to do is you have some code. So luckily Azure provides us with all this code. We do not have to worry about it. We just do small modifications here and there so that everything fits properly in a pipeline. So we ask Azure to predict on this file. It gives me the file is French. And before that, I predicted all. So we have a softmax layer, as we mentioned. So we are returning the output from the softmax layer. So I have set the code to display all the probabilities. So for English, it is 0.008. For French, it is 0.99. For Spanish, it is even smaller than English. So you get the output for French over here. And what you'll do is, what the logic works is you have three probabilities. You'll apply an argmax function to get the index of the one with the highest probability. So in this case, we have the index one has the highest probability. And using index one, you'll pass it to a reverse encoder. If you remember in the training phase, we saved the label encoder. So we save that, and in inference step we use that encoder to reverse encode the one value back to French. And similarly, we have test for the English data. Let's hear the English data.
He proved to be effective but injury prone in his years with Detroit.
So here you can see the audio has some sort of weird noise in the background. At the same time, there's a bit of accent to the voice. So let's see if the model is able to correctly identify it. You can see cause of the accent, the probability is kind of less, like not less, I wouldn't call it less, but it is not near 0.99. But because of the accent as a disturbance, we still have a lesser probability, but still greater probability compared to the others. And we were successfully able to identify it as English. Now, same logic with Spanish.
Su segmento era formas especiales.
You can hear the Spanish, and I'm running it again. Here we can see the probability, if the audio was quite clear, the probability of it being Spanish is 1. So this is inference. At the same time, every time we ping the model, you can actually also see the logs of what the endpoint is working in this section. And here you can see the overall, it takes about 15 seconds for us to make a 15 milliseconds for us to make a prediction, which for a neural network is actually really good. So that's the inference. Thank you.